This is Lesson 24 in our Calculus 3 series, Applications of the Double Integral. In the last few lessons, we've seen that double integrals can be used to find volumes under surfaces. We also saw in Lesson 23 that the double integral can be used to find the area of the region over which you're integrating. In this lesson, we're going to see 4 more applications of the double integral, and then in the next lesson, we'll see another. So here we're going to talk about the average value of a function over a given domain. We'll talk about the computation of total mass of a thin plate given its density function, computing the center of mass of a thin plate given its density function, and finding the moment of inertia of a thin plate given its density function. And in the next lesson, we'll talk about finding surface area. So let's start with the average value of a function over a domain. Consider this surface, f of xy equals xy squared, over the right half of the unit disk. So the gray is our domain here, and then the blue is the surface that we have. We want to talk about an average value for this function over this domain. So what is it that we're looking for? We're looking for a z value, we're looking for a height, under which the volume would be the same as the volume under this surface. So for example, for this function, this height here where this red plane is, that's the average value. The volume under the surface over that region is the same as the volume under that plane over that region. So we want to talk about how to compute this z value, this average value. We're looking for an average value for z such that we said the volume under that plane is the same as the volume under the surface. So we want the average value multiplied by the area of the domain to be equal to the integral of f over that domain. So how can we solve for this average value then? We divide both sides of this equation by the area of D. So to find the average value for f, we're going to take 1 over the area of D times the double integral of f over d. So for the example above, the average value of the function f of xy equals xy squared over the right half of the unit disk looks like this. We're going to take the area of our domain, so that's 1/2 the area of the circle. Our radius here is 1, so we get pi over 2. That's the area of our domain. And now we want to take 1 over that area multiplied by the double integral over d. Now describing this region, we'll take x going from 0 to radical 1 minus y squared, and then y going from -1 to 1. So we'll integrate on x first. X goes from 0 to radical 1 minus y squared, and then integrate on y from -1 to 1. Or if you want to describe this region in polar coordinates, we can integrate in polar coordinates. In that case, we would have the 2 over pi that comes from 1 over area, and our integral would look like r going from 0 to 1, and theta going from -pi over 2 to pi over 2. And we plug in x equals r cosine theta, y equals r sine theta, and then for our area element we have r dr d theta. Now, these are both reasonable computations to make, so as an exercise, I would like you to solve both of them. You'll notice either way, you get 4 over 15 pi. And that's the average value for f over this region. So that's the height of that red plane. Let's take a look at what we need for mass calculations. Recall that density is mass over volume for solids in R3, but when we're talking about a thin plate, we give density in terms of mass per unit area. And when density varies through the region in R2 or varies throughout our thin plate, we talk about a density function. This is rho of x and y. And then the total mass over region D, and region D describes our thin plate, the total mass is going to be the integral over d of that density function. Because notice, mass here is density times area. we have density times area. But what's happening here is that our density is not constant, our density is changing over the region. So we need to integrate over this region, and what we're multiplying is density times this incremental area. Think about the Riemann sums. The Riemann sums break the domain into rectangles, and on each rectangle we're multiplying a density times an area and getting a mass. So we're multiplying our representative density for that subrectangle multiplied by the area of that subrectangle and adding that all up. And so in the limit, that becomes this double integral. So now let's find the mass of a thin triangular plate bounded by the y-axis and the lines y equals x and y equals 2 minus x if rho of xy is equal to 6x plus 3y plus 3. Now the first thing I want to do is talk about this density plot here on our region. This kind of plot shows the different density values along this plate. Up until now, when we had a function of x and y, we considered this function value to be a height and talked about a surface in three-dimensional space. But here, having the density value represented as a height in three-dimensional space isn't very useful for us. We want to know along this two-dimensional plate, where is there a high density area, where is there a low density area. So this density plot uses a color gradient to give us an idea of where the high and low points are, and any kind of pattern that we might see in the density values. So this density plot gives us an idea of how the mass is distributed, and what we're looking for is a total mass for this thin plate. So we're integrating over this region the density function. So we'll take y going from x to 2 minus x, x to 2 minus x, and then x going from 0 to 1. From 0 to 1. So integrating first on y, we're here, plugging in our bounds, doing a bit of simplifying. We get 8. So consistent with whatever units the density was given, the mass is going to be 8 units of mass. Now let's talk about calculating the center of mass of a thin plate. So this is going to be the point on the plate at which it can be suspended and remain in static equilibrium. So that means that it's the point at which you could balance the plate on your fingertip. So for the x-coordinate of the center of mass, we need the total mass of the plate multiplied by this x-coordinate to be the same thing we would get if we multiplied x by the density and integrated over d. In other words, remember that density times area is a mass calculation, so if we did this at each individual point over d versus just taking the total mass multiplied by this x-coordinate, we should get the same thing. That's how we're finding this x-coordinate of the center of mass. Similar for the y-coordinate, we're multiplying y by the density and integrating here. So that gives us these formulas for our center of mass, the x-coordinate, the y-coordinate, and we're dividing by m here. M is the total mass of the thin plate. So for the plate that we just looked at above with the triangular region, and density formula, rho of xy is equal to 6x plus 3y plus 3, we found that the total mass is equal to 8, and so now let's find the center of mass of the plate. So for our x-coordinate, we've got 1/8 multiplied by this integral x times the density function. So we'll distribute our x. I've got it set up in y, so we'll integrate with respect to y first. Plug in our bounds, subtract, do a bunch of simplifications. And we get x bar is equal to 3/8. That's the x-coordinate of our center of mass. For the y-coordinate, again we have the 1/8, but now we're multiplying y times the density function. So we'll distribute here, and we'll integrate with respect to y. Simplify here. Now we'll plug in our bounds. And simplify. Then integrating with respect to x and plugging in our bounds, we get 17 over 16, and that's y bar. So that's the y coordinate of the center of mass. So that tells us that with the given density function, which is telling us the distribution of mass over this thin plate, this point here, 3/8, 17/16, that is the center of mass. That's where you'd want to balance that plate. Notice though in these calculations, if the density function is equal to 1, then the mass just becomes the area of the domain. And then x bar becomes 1 over the area of the function x. So that's just the average value of the function x over that domain. And similarly, y bar is 1 over the area integral of y over that domain. So that's just the average value of the function f of xy equals y over that domain. So for example, find the center of mass of the right half of the unit disk with constant density equal to 1. The right half of the unit disk is here. Now we're expecting that if we're looking for center of mass and it has a constant density, we're expecting that center of mass to be somewhere along the x-axis. In other words, the y coordinate, y bar, should be 0 by the symmetry of the shape and because it has constant density. And you can make that computation as an exercise, and I'm sure you'll get 0. But let's take a look at the computation for x bar, the x-coordinate of the center of mass. We've got 1 over the area. This is the same area we had above, and that's pi over 2. So we have 1 over pi over 2 times the integral of x over this region. So I think it's easiest to integrate this in polar coordinates. Our radius goes from 0 to 1, our theta goes from negative pi over 2 to pi over 2, and x is equal to r cosine theta, and dA is r dr d theta. So we've got r squared here that we're integrating, so we get r to the third over 3 cosine theta, plug the 1 and the 0 in for r, so we have 1/3 cosine theta that we're integrating. And the 2 over pi on the outside gives us 2 over 3 pi sine theta. Plugging in our bounds and subtracting, we get 4 over 3 pi, which is approximately 0.42. So on our unit disk here, our center of mass would be approximately here at 0.42, 0. Let's talk about now the moment of inertia. The moment of inertia is the tendency to resist angular acceleration. So if we're talking about angular acceleration around the y-axis, the moment of inertia looks like this. We'll call that I sub y, and that's the integral over the domain D that describes the thin plate we're talking about of x squared times our density function. And around the x-axis, we have Ix integrating y squared times the density function. So let's find the moments of inertia of the triangular region bounded by x equals 0, y equals 0, y equals 1 minus x. So that's this region here. With constant density now, rho of xy is equal to rho. So this is a constant now. So for the moment of inertia around the y-axis, we're integrating x squared times rho. And setting this up dy dx looks like y going from 0 to 1 minus x, and then x going from 0 to 1. So integrating with respect to y, we're here, plugging in our bounds, and simplifying, integrating again, plugging in our bounds. We've got rho over 12. So this value represents the tendency of this object to resist angular rotation, and we're talking rotation about the y-axis. Now what about the moment of inertia around the x-axis? Based on the symmetry of the region and that there's a constant density throughout the region, we expect the moment of inertia around the x-axis to be the same as the moment of inertia around the y-axis, the same rho over 12. Again, because of the symmetry of the region with respect to the x and y axes, and also because the density is constant here. So let's take a look at that computation as well. We've got rho y square here. Again, y goes from 0 to 1 minus x goes from 0 to 1. Integrating on y, plugging in, integrating on x. I did a little u substitution here instead of multiplying that out. And again, we get rho over 12, which is what we expected. So here we've seen the average value of a function, the computation of total mass of a thin plate, center of mass of a thin plate, and moments of inertia. And this concludes our lesson on applications of the double integral.